and welcome to the 6th lecture, Lattice Boltzmann methods in winter 2023. I give you here a small appetizer of what you can do with Lattice Boltzmann if you treat it well, yeah. So, because I'm always told we are doing too much theory here, today we are going to do, we are almost in the middle of the semester and we have a very central lecture in this series, because now we have gathered enough information that we can actually deal with the real analysis of the Lattice Boltzmann method. So now you saw the colorful fluid dynamics, and now we come to the real interesting stuff, that is the analysis of the Lattice Boltzmann method with asymptotic analysis. So today we go through these things here: Taylor expansion, asymptotic expansion, and we look at acoustic and diffusive scaling, and then we will derive the equivalent partial differential equations of the Lattice Boltzmann, of the Lattice BGK method. So I've written down a little bit of text. I don't know whether it's not completely required that you write this down. I just want to start with what we are going to do. So the asymptotic analysis is a method that we can use to analyze numerical methods without actually executing them. Yeah? So nowadays there's a lot of talk about data-driven methods and data-driven analysis. Yeah, that's all fine. The asymptotic analysis is the other end of the spectrum. There you don't need to do any simulation. You just look at the theory of your method. And what you can do with this is you can derive how your method will converge and what is the actual partial differential equation that you are solving. So in a sense, asymptotic analysis is also an inverse method, in that sense that it is not used primarily to derive new methods, but it takes an existing method and tells you what the existing method does. Of course, you could also do it in a hybrid way. So you assume a method where not all the parameters are yet specified, yeah, and then you can get them out of the asymptotic analysis. This is what is written here. It's a completely algebraic method, and therefore you can use it to obtain also unknown parameters. Also compared to other analysis methods, for example, what is done what is this? For Neumann analysis, yeah, this method does not rely on linearization. So you can look at nonlinear problems, as is the Navier-Stokes equation or the Boltzmann equation, of course. As I said, it's not based on data, not at all. And it is also not only applicable to the Lattice Boltzmann method. So actually, I always think that other people should use such a method too. Some do. It's not completely common in other fields. Okay. So after this, let's jump into the lecture, which is the challenge. The challenge of today, or the challenge of the day, is that we take now our Lattice BGK equation and we derive or method and derive the partial differential equation, the PDE, that is solved specifically by the D2Q9 LBGK methods. This can, of course, also be applied to other methods, but we start with something simple, so something relatively simple, that we get the idea, and then we can apply this to other methods too. So say this method we are talking about is using the D2Q9 lattice, and I believe we have already introduced this nomenclature. We have the populations with two indices in our case, F1, 0, and using the Miller indices F-1, 0, and of course F0, 1, and F0, minus 1, and then, for example, here is F1, 1, and here is F-1, minus 1, and so on. And of course, here in the middle, there will also be an F0, 0. So this is, we have populations Fi and J, with I and J are in -1, 0, and 1. So this is the model we are using. And on this lattice, we will use the lattice Boltzmann equation. The lattice Boltzmann equation, which can be written in different formats. Use a specific format that makes our life simple, called the lattice Boltzmann equation, now equation 6.1. And I put everything on one side. So I say 0 is equal to Fij. So this is the pre-collision state, which I shift here by half grid spacing. Let me just write this down. So we have a unit vector in x direction and a unit vector in y direction. These are these Ex and Ey. They shift the distribution by a half grid spacing. Yeah? So we are remembering the characteristic diagram, yeah, that we are always half a grid spacing and half a time step, so that the data is stored half a grid spacing and half a time step away from the collision, right? And the time x, the place x and the time t is the location and the time of the collision, yeah, not this streaming. So this is also t plus delta t half, right? So and this is our pre-collision state, and from this we subtract the post-collision state. So remember, the streaming turns the post-collision state into the pre-collision state, right? So this is, both of them are the same. This is why I'm subtracting them and get to 0, yeah, in order to get an equation, because we call this the lattice Boltzmann equation. So it needs to include some equal sign, yeah? So what happens here is that we've moved this 1/2 grid spacing to ahead, yeah, and 1/2 time step ahead. So we have to go 1/2 time step backwards in the other case, right? So then this is minus. So the reason why we are doing this is, by the way, not the standard way of doing this. I modified this myself compared to how it's usually done. The reason for doing it this way is to make it symmetric. This will simplify the analysis a lot, yeah? So now this is 1/2 time step before. I mean, you easily see you could easily shift both of them to one side, yeah, and then this would be the same thing. But now we locate our timing at the collision time, and this x is the collision place, the center of the lattice, and t is the collision time. Not the time it takes for the collision, but the time at which the collision takes place. Yeah. So these are unit vectors, and because they are unit vectors, they have the length 1. Okay. So what does this lattice Boltzmann equation not specify is how we actually do the collision. Yeah. So collision can be done in different ways. We'll talk about this in later lectures. But here, we'll now use the very simple version of the BGK equation that we have to add. So if we use a different collision model, then we have to replace this part here with the other model. So we'll call this collision model 6.2, and this says that Fij asterisk at the time of the collision, at the space of the location of the collision and at the time of the collision, yeah. Post-collision, star is the post-collision, so this is post. Post-collision minus the same thing in pre-collision. So this is the change, obviously, yeah. So the change is related to omega Fij equilibrium minus Fij. So this was the BGK model. Okay, so what can we do? We do what we always do in numerics. We use the Taylor expansion. Taylor, never. We use the Taylor expansion of the equation up there, 6.1, at the location x and t. So you see that these populations are not located in x and t. Yeah. So we have to make a Taylor expansion of them, and then we get these derivatives. So this will be called equation 6.3, and okay, it starts with 0 because we have 0 on one side, and then we do the Taylor expansion, and the Taylor expansion now is of course a Taylor expansion in 3 dimensions, yeah, because we are moving in x, we are moving in y, and we are moving in t, right? So this means all of them I put here a single sum sign, and I will iterate over m, n, and l. Yeah, so today we'll see big sums. So we do the sum of all of them. I mean, here now we have to be very firm in how a Taylor expansion in several dimensions looks like. I hope this is more or less clear. So we have m factorial, n factorial, and l factorial. These are the iterators, and we are using. Okay, and then we have the distance we are moving. The distance is delta x half for the spatial movement, right? And we associate t with m, x with n, and y with l. Okay, so this means the two in space are n plus l. Yeah, so we'll have them here, and we have the one in time. This is also a half time step. This is m. So and now we get the derivatives. The dt. The dt is the mth derivative, right? And dx is the nth derivative, and dy is the lth derivative. And now comes, okay, so what I did not include in here is this direction I, right? So then I have to write this here, I by the power of n, and j by the power of l, yeah? Fij. Now I don't write these things getting large. Obviously, this is now at x and t, right? So I'm not writing this explicitly. Okay, so this is the positive guy here. And then we also have the negative guy, so starting with a minus, and now it becomes a little bit tricky because here is a minus, right? And also with t is also a minus. Yeah? So this may be going in negative direction, but we are taking this to the power of n and l. So obviously this will now depend, before we later depend, we can simply write this is minus, I mean it's minus 1, yeah, minus, it's minus e. Sorry, minus e by the power of n, yeah, and it's minus j by the power of l. So, and what's one thing that did not appear here was the time, yeah, because the time is here positive. So I could just say 1 by the power, so it would just be 1 by the power of m, and 1 by the power of m is always 1. This is why I didn't write it, yeah. But here is minus 1 by the power of m, right? You see it? Yeah. Okay, so then it's minus 1 by the power of m. And this goes into this post-collision state ij, Fij star. So this is the Taylor expansion of everything, and all of this is 0, but I will call this in order to make it mobile, yeah? I mean, put everything in a variable. I call this thing capital T, yeah? So that I can actually deal with this. Okay, looks complicated, but it's getting, should I say worse? It's getting interesting again. So here, what is a little bit impractical still is that we still have these populations, yeah. And what is the expected outcome? What outcome will we expect from the? What are we actually looking for? No, not from the Taylor, from the entire analysis. So we want to derive the partial differential equation that we saw. Which partial differential equation would that be? Yeah, but so yes, true. But what is the partial differential equation that describes the velocities? So what partial differential equation you usually Navier-Stokes equation? Yeah. So the entire exercise is we are looking for the Navier-Stokes equation in the Lattice-Boltzmann method, right? So this is what we expect. So now we are still in Boltzmann world, still in kinetic world, where we have these populations F. And later we want to have U and pressure. So now we have to make some transformation. We know that U and pressure are moments. Right? This is what we already know. So we have to turn these things here into moments, and this has, and herefore we have to remind ourselves. So now we had this 3 or 4 times already, but again, we have to remind ourselves about these raw countable moments that we had defined as MAB is now for the lattice, it is the integration, because it is moment is an integration, but we're integrating a discrete function. This makes it a sum, right? So we are summing over I and j that goes from -1 to 1 Fij I by the power of A and J by the power of B. And by the way, we assume, so this is an assumption that we have to make, that 0 by 0 is 1. I mean, this is controversial, but for the purpose of this derivation, this works only under this condition. So this is now the assumption that we make. Okay. Now, when this actually would be the pre-collision moment, right? So then we can also write the post-collision moment with the star here. That's very simple, -1 to 1. The same thing on the post-collision distribution. And we have introduced this MAB. We have introduced the quantities with the overbar. Yeah, so last time last time or the time, the lecture before, I don't remember. We've introduced the populations with the overbar. Now I introduce the moments with the overbar, and the population with the overbar was the average between the pre and the post-collision stage. So the average is like this, and then it goes into I by the power of A and J by the power of B. Now we have all the three of them also in moments, right? The pre-collision moment, the post-collision moment, and their average. So now if we define the sum of pre and post, then we somehow destroyed pre and post, so we have to, in order to keep all the variables, we also have to define the opposite, which is the difference between the two. And the difference between the two is supposed to be a minus, it's not visible. This is also, so this is post-collision minus pre-collision. So the change that happens during collision, right? And this we call omega. Okay, now this is something that, and most of this, I mean, up until omega, this is what we already had. Now what we do next is we take this equation 6.3 and actually take moments, raw countable moments of the equation. So this is, take moments of 6.3. So this is why I called everything here t, right? So because then the equation looks like this: 0 is equal to I, j is going from -1 to 1, t times I by the power of A and J by the power of B. So everything that is written here in this equation, I will multiply by IA and JB and take the entire sum over this. So this will lead us to the following equation. I have to write a little bit small today because some of these equations are pretty long and I don't want to write into too many different lines. Say I put here 0, then there is this sum, this outer sum I and J starting from -1 to 1, and then we sum over the Taylor series M, N, and L to infinity, starting from 0 to infinity, and then we have this 1 over m factorial, n factorial, l factorial. Then we have again delta x 1/2 n plus L, delta t 1/2, and then all the derivatives, the mth derivative in time, the nth derivative in x, and the lth derivative in y. So now comes Fij, and now you observed that I have not yet written this I by the power of A and J by the power of B. Now, because here comes times I, right? And there is in the above equation here is an n. And now, because we multiply all of them with I by A, yeah, this becomes I by the power of n plus A. Yeah, very simple. And the same thing J by the power of L plus B. So it continues with minus I by the power of n and I by the power of A. Now it's a bit more complicated because the one comes with a minus and the other one does not come with a minus. And here minus J by the power of L and times J by the power of B. And then this continues with minus 1 by the power of M, and this goes into Fij post-collision. Okay, so the important thing to observe here is that we see the definition of moments, right? Yeah. So here, because we have an outer sum, we can put the sum inside. Yeah. So we can take basically we take this sum and put it into here, and we'll also put it into here because everything here is otherwise linear. Yeah. And then we execute this sum and we get the moment. Yeah? And now there's an interesting thing which I do it now a little bit quicker. I mean, I don't want to write everything in very detail now. The thing that you notice, we have here alternating positive or negative signs, right? So we'll either have, depending on what n and what L is, we'll either have the sum of the two or we'll have the difference of the two, alternatingly, right? And now this can be written down in equation 6.4 as 0 is, now I've executed the sum, so this is why I start from the second sum. 1 over m factorial n factorial L factorial. So I'll have to repeat a few things here. First, n plus L and delta t half. Oh, I guess I forgot the m here, right? Yes, I forgot the m here. By the power m dt m dx n dy L. So, and now we'll have the moments, so the average moment, which is the sum of f and f star, yeah, and this goes, and the moment that we get is a plus n in x, and b plus L, yeah, because we'll have these sums here. And this, okay, this requires a little bit of algebra, and I've not checked it yesterday, so I just write it down. So this is what comes out, right? So I hope it's correct. We have 1 minus 1 by the power n plus L plus m. Yeah, you see, when this here is even, this will drop out. If the exponent is odd, you will have it twice, right? So every second one drops out, and otherwise you get them twice. And something similar happens with the omega. Here again you have A plus N plus B plus L, and then we also have something like this. This is 1 plus minus 1 by the power of n plus L plus m. So basically what you see, so there's a half here, which is probably a little bit kind of an inconsistency, because if you look back at the definition of omega, or the m, we take the averages of m, right? So we add them together and divide by 2, but in the omega it's just a difference, so it's not divided by 2, and this is why we have a division by 2 here in the equation. So now what you see is that depending on on the value of n, L, and m, either this here will be there or this here will be there, but never both, right? Because there's once minus and there was once plus, right? So interesting. Okay, so this is what comes out so far. Now, this is a position where with which you can already do a lot of analysis, and some people stop there. Yeah, but still we have a little bit of problem, and this is related to our smallness parameters here. As we have two different smallness parameters. And we have, so this is one problem, and the other problem is we have an infinite sum. Yeah? So these are problems that we still have to tackle. And in order to get rid of the infinite sum, we do now something that's called the asymptotic expansion, which is the cornerstone of an asymptotic analysis. So you can do analysis just by Taylor expansion alone. It's also useful, but the more rigorous way of doing this is by so-called asymptotic expansion. Okay, so always remember the asymptotic analysis has two expansions. We have the Taylor expansion and we have the asymptotic expansion. Now, what actually is the asymptotic expansion? Before we talk about the asymptotic expansion, we have to talk about the smallness parameter. So there is a smallness parameter, epsilon, is a discretization dependent or specific scalable parameter. So the discretization scales with this parameter. So typically what we mean by this is either the grid spacing or the time step. Yeah, so this is what a scalable parameter of your numerical scheme usually is. Okay, and now very, very general. So people who come to my lectures will know this. Every professor has one favorite thing to tell all his students, I guess. So there's always one thing that they all say in all lectures, and this is my favorite thing. Yeah. So what is a numerical approximation? A numerical approximation is you have a function phi of an independent variable or a set of independent variables x and a smallness parameter epsilon. And this is supposed to be a function f. So this here, this is the approximation. So the phi is the approximation and f is the function being approximated. So usually the problem is you cannot evaluate f because f may, for example, be the Navier-Stokes equation, so you don't know about solutions of the Navier-Stokes equation. So you take a replacement of the Navier-Stokes equation, which may, for example, be a control volume discretization of the Navier-Stokes equation. Say this is an approximation, yeah, and this now will give you obviously the solution of the Navier-Stokes equation, the answer of the Navier-Stokes equation plus an error. And in order for this to be an approximation, the error has to be has to fulfill some properties, namely that you can write it as a series expansion of the smallness parameters. So there's a series of error terms. So, by the way, I mean, you could always say everything, so you could just throw out a number and say this is an approximation, yeah, to anything, and because this plus an error is the real thing, right? Yeah, but you wouldn't accept this because you don't have control over the error. This epsilon gives you control over the error, and you will only call this method consistent or an actual approximation. So if it has this condition, so it's called, the method is called consistent. So then it's, when it's consistent, then it's actually an approximation. If the limit for epsilon going to 0 for phi epsilon, x and epsilon is f of x. This means that in the limit of epsilon going to 0, the error is 0. Then it's an approximation, right? So in the limit of infinitely small grid spacing, in the limit of infinitely short time step, you actually get the solution. So, meaning, yeah, let me write this down. Numerical approximation phi, x, and epsilon is the truth, or what the ground truth, whatever. So, the real solution plus a hierarchy. And this is important, so it's not just any number, but the hierarchy of error terms. And they are separated by powers of epsilon. What does this mean? Very abstract. Now suppose we look at our moment MAB, right? So this moment MAB is supposed to give us first the actual solution at the leading order and then a hierarchy of error terms. So this means we could write this guy like this. We start at n equal to 0 and we go to infinity. So there are infinitely many, so the series infinitely many error terms. And they come with epsilon by the power of n. And then we write a, b, and here in brackets, nth order. Right? So we get these things, they are constant. And now we have the dependency of epsilon in this in epsilon by the power of n. So the same thing can of course be done also for the collision, the omega here, n from 0 to infinity, epsilon n, and this is omega ab at the order n. So, what is very important to keep in mind, these MAB and omega AB n, so this is extremely important. They are not functions of epsilon. So, very, very important. How comes they are not function of epsilon? Well, the functionality from epsilon is put into the series expansion. Yeah? So, MAB is a function of epsilon, obviously. Yeah? But we express it in a series where we have constants times epsilon by power n. Yeah? So, we demand from this that all the information is expressed in this way, and that MAB n of the order n itself is not dependent on epsilon, but all the functionality of epsilon is here in this epsilon by the power of n. Yeah? So this is very important, so that there is no hidden dependency, but we express the dependency in this series. Okay, let's look at something specific. Say we want to solve the Boltzmann equation or the Navier-Stokes equation. So what is going to come out of this is, for example, the density and the velocity. They will come out of our LBGK. So, and now we'll have a rho. So this is the outcome of our simulation, the density rho, right? And the density rho, it must be possible to write this as a density rho to the 0 order plus epsilon, rho to the first order plus epsilon square, rho to the second order, and so on forever. The same thing with the velocity u. Velocity u comes to 0 order plus epsilon u to first order plus epsilon square u to second order plus ... Okay. Great. The thing that's just missing is, what is epsilon? What is epsilon? Any idea?
It's the error.
The what?
The error.
No, epsilon is not the error. The error, this is the error. The epsilon is epsilon times. Okay, so what would be the error? Yeah. So this guy, these things here, these are the errors, right? This is an error. The epsilon is the smallness parameter. But what is the smallness parameter in a partial differential equation? Problem is, we have discretization in space and we have discretization in time. So we have to make a decision, and this decision is not unique. And actually, there's controversy about this. Yeah. So, what's the problem? LBM has two numerically small parameters, namely the time step and the grid spacing. Delta x and delta t. So the thing is, we want to have only one epsilon. And for having only one epsilon, there are different possibilities, obviously, because we have two choices. Actually, we have more than two choices. We have infinitely many. So we have infinitely many, but there are two obvious and two which are in literature in use. And they have, so say there are two choices that actually have names. They are so obvious that they have been given names. Yeah? And the first one is the acoustic, and the second is the diffusive scaling. Okay, so what is the acoustic scaling? The acoustic scaling is the very obvious. We say that delta x is proportional to epsilon, right? So grid space, the smallness parameter is just proportional to the grid spacing and the time step, okay? So, which means that delta x by delta t is regarded as a constant, okay? So, this also implies that the speed of sound, which in Lattice unit is here c. So we've derived this from the aliasing. Yeah, is 1/3 delta x by delta t, and this also is a constant. Okay, which means that the speed of sound is invariant under scaling. The speed of sound is invariant under scaling, and this is why this is called acoustic scaling. Yeah? And by the way, if you want to do acoustic with Lattice Boltzmann, this is what you are going to do. You'll use acoustic scaling. However, there is also a problem with acoustic scaling. And this is related to our two-dimension, what I'm writing, two-dimensionless numbers in the compressible, I have to say, in the compressible Navier-Stokes equation, only in the compressible Navier-Stokes equation. Namely, the Mach number, this is related to the compressibility here. The Mach number, Mach is, say, a unit, so I write this with a star, saying this is the physical velocity. I call it the physical velocity because this has the physical velocity scale, because we are using a lot of dimensionless variables in numerics. So usually it's done like this. You define your dimensional. You start with dimension with variables having dimensions, and then you make them dimensionless. And then because you have to give it a different name, you put an asterisk, and then the dimensionless is the asterisk. And then what people do is they drop the asterisk because they have to write all the time about the dimensionless quantities, and they don't want to put the asterisk there. So because we use all the time dimensionless variables, I've decided to give, when I'm talking about dimensional variables, I put the star there. Yeah? I'm doing it a little bit the opposite way. So this is dimension taking variables, and the second is, of course, the Reynolds number. Reynolds number, so it's R, and this would be the scales. Okay, in principle I have to put an asterisk here too. So this is the physical length scale. Okay, and this new viscosity, new with star or without star is CS square 1 over omega minus 1/2 times delta T. Yeah, so this is how we come to the viscosity. Yeah, speed of sound squared times delta T and 1 over omega minus 1/2. So we can write the Reynolds number as U star L star divided by CS square 1 over omega minus 1/2 delta T. And this we can again write as the Mach number times L star divided by CS 1 over omega minus 1/2, and here's the left, we are left with delta T. So CS is, as we discovered, scale independent, yeah, because it's delta x by delta T, they scale the same thing, so they will be together scale independent, but we are unfortunately left with a scale dependent parameter delta T here, inside the Reynolds number. And this is a little bit a problem, because the Reynolds number is a physical constant, right? So a physical constant should not depend on the grid spacing, right? So we have to make it independent of the grid spacing. Reynolds number must be independent of grid spacing. So, how do we do this? Let's say we take everything that is independent, that actually is scale independent on one side, to get a better overview. So this means we could write this as Reynolds number times CS. So I'm multiplying this by L star Mach, and this is 1 over omega minus 1/2, and this into delta T, which we can translate in 1 over omega being equal to L star Mach number Reynolds number times CS. So this here is obviously, this is scale independent. So by scale independent, we always mean the grid resolution, yeah, not the physical resolution. Yeah, physics is given, yeah, as our problem. Yeah, we have a car, we should simulate a car, we should simulate an airplane. The Reynolds number is given. Yeah, what we can choose is the grid spacing. This is our scale. That's our scale. Grid spacing in time step. And here we unfortunately have a time step left. So this here is obviously scale dependent. And then we have a plus 1/2 still. So we have to make this guy, the entire thing here, scale. In order for this to be scale independent, this omega obviously has to be scale dependent. Yeah? So omega depends on the scale, on delta t. Yeah? So this is in acoustic scaling. So acoustic scaling epsilon is proportional to delta t. This is what it means. Omega is a function of the resolution. Okay, I'm stressing this here. So you're a poor guy, yeah? So you hear this the first time in your life, probably. Yeah. And I'm stressing this so rigorously because this is one of the most persistent errors that is made in this expansion. Yeah? The thing is the following. If we do the asymptotic analysis, we have to be absolutely sure that we know whatever depends on smallness parameters. Yeah? Now you have this innocent looking omega in it. Yeah? And you could assume, and this is what many people do, it is something that does not depend on the scale. But this is not true. The omega depends on the scale. Yeah? And so you have to take the dependence of the omega from the scale into consideration if you make the analysis. Otherwise your analysis is wrong. Right? So this is a very common mistake, actually, in particular with mathematicians. In particular with mathematicians, because they don't think physically. Yeah. So they think, okay, so there's a parameter. The parameter could be anything. But the thing is, we are solving a physical problem, and in our physical problem, these parameters, the Reynolds number, is a constant. Yeah, because we look at something specific, not at any Reynolds number, but at a specific Reynolds number. Yeah? So, let me write this down. So, ignoring I spent more than 10 years, I will say 15 years or so, explaining this to the same guys. They always say yes. And then next year they do the same thing. I mean, it's not students, professors, right? From all over the world. Ignoring the dependence of omega on delta t in acoustic scaling is one of the most persistent errors in LBM literature. Though they write papers making claims, coming to conclusions following this. and it's not, it's not correct. Okay. Okay, so there is something else that we have to take into consideration. In acoustic scaling, the lattice speed is not asymptotically small. Compared to not asymptotically small, sorry. And the rest of it. So that because delta x by delta t is a constant. Okay, what does it mean? That means if you have an error in velocity, as if you remember, for example, this is just one of the possible examples, when we derived the aliasing of the third order moment, M30, yeah? We saw that we are missing there a term u by the power of 3. Yeah? And then we said u is small, therefore we can neglect this. Yeah? But now, delta x by delta t is const. So it is not actually small in the sense that if you refine your grid or you make your time step smaller, then the error u by the cube has exactly the same size. It's not getting smaller. This is what we mean by asymptotically small. Asymptotically small does not mean that the value is actually small, but it means that if you make the smallness parameter smaller, then the error is getting smaller, right? But here, u is a constant, is not dependent on the scale, so u cube is also not depending on the scale, so the error is not getting smaller if you refine. Even if it may be small to begin with, but it's not getting smaller. And because it's not getting smaller, there is no convergence, right? If the error is not getting smaller, if it always stays the same size, you have no convergence. And this is the problem with this acoustic scaling, even though it's used a lot in literature, especially if you deal with acoustics, which you could do, but LBM does not converge. Yeah, this is a ugly fact. Yeah, it's not converging in acoustic scaling. It just does not. So what people do is they put on top of this additional assumptions. I mean, they just assume that velocity is small, right? Yeah. So but you can assume whatever you want, yeah, but it doesn't actually converge. So they do some assumption and then it converges. Okay, so now I've bashed a lot on acoustic scaling. Now we come to the one that we are actually using here. This is the diffusive scaling. Diffusive scaling. So what we want to have is that omega should be lattice scale independent. Yeah, make omega independent of the scale. That's the challenge. While at the same time the Reynolds number should be constant. So Reynolds number is U star L star CS 1 over omega minus 1/2 delta t. So hence it is supposed to be constant because it is what is defining our physical reality. Now the CS square, we can also write the CS square, sometimes write this as theta, theta being the dimensionless temperature. Okay, it's the one thing that is 1/3 in lattice Boltzmann usually, yeah, but it's related to the temperature. So we know the speed of sound square is related to the temperature and the gas constant, but we consider the gas constant to be 1, right? So, okay, if we put this into this thing here, then we have U star L star divided by theta, and here we have, no, I'm not writing it this way, delta x squared by delta t square, 1/omega minus 1/2 delta t. So, and this is still considered to be constant, and also omega is considered to be constant. So, and if omega is constant, this is when delta x square is proportional to delta t, right? So we divide once by delta t, and if delta x is now proportional to delta t, then everything here is in order. The one thing that you could say is probably not in order, or depends, yeah, how you see it. CS is obviously the square root of delta x by delta t, and this now will become epsilon by epsilon square, which of course is 1/epsilon, which means that in the limit epsilon is going to 0, CS is going to infinity. So is this a good thing or is it a bad thing? A bad thing. It can be a bad thing and it couldn't be a good thing. It's a bad thing if you deal with acoustics, because your pressure waves, the Mach number obviously depends on the resolution, right? However, if you think incompressible Navier-Stokes equation, where your Mach number, so in incompressible Navier-Stokes equation, you assume that your Mach number is 0, yeah, or that the speed of sound is infinitely fast, yeah, and this is what we have here. So if we use diffusive scaling, we are done with acoustics, cannot deal with acoustics anymore, but we are in the limit of the incompressible Navier-Stokes equation. Okay? And let's see whether we get to the incompressible Navier-Stokes equation in that way. So, why is this the simulated? So our velocity that we simulate is now small, asymptotically small compared to the speed of sound and the lattice speed. This means also that errors in velocity cube, for example, will get smaller with finer crits, right? Yeah. So these errors will disappear. So to the speed of sound, and we have no acoustic errors and no Mach, or let's say we don't have none, but they become smaller the finer crit we use. Okay. Of course, yeah, as we just said, the Mach number is no longer is not scale invariant, so we are done with acoustics. So our speed u star is u delta x by delta t. So this u here is our dimensionless. Our dimensionless velocity. This means that our solution, there's an interesting thing, that our solution what does it mean for our solution? Our solution now has a constant part, which is actually not the solution, but the solution is the first order part. So this is our solution. Why? Because the velocity itself becomes smaller with the grid spacing, with the smallness parameter, right? So then this means that this part here, the constant part, is not what we are looking for, but we are looking at the first order and not the zero order. And then comes the higher orders, they still remain to be errors. Okay. So now, after this big detour about asymptotic analysis, we now come to the asymptotic expansion of our Taylor expanded moment equation. Yeah? So we include the asymptotic expansion into the Taylor, in the already Taylor expanded equation. Expands. Asymptotic expansion of LBGK in the diffusive scaling. Okay, now we have to go back, remembering equation 6.4. I'm going to write equation 6.4 because it's some time ago already, right? So it's 0 was equal to the sum over m n l is equal to 0. 1 over m factorial, n factorial, l factorial, delta t half, m delta x half, n plus l, and dt m dx n dy l. Now comes the average of the moment ma n plus n, b plus l. This goes into 1 minus 1 by the power of n plus l plus m. So I'm doing this in 2 dimensions only, because in 3 dimensions you have even more indices to deal with. Omega a plus n b plus l, so 1/2, and this goes into 1 plus minus 1 by the power of n plus l plus m. So, closing the brackets. Now, we define an equation 6.5 in which we introduce the asymptotic expansion of m and omega. Yeah? So, again, a lot of writing. The sum over m, n, and l equal to 0 to infinity, 1 over m factorial, n factorial, l factorial. Now, we said that delta t and delta x, yeah, they are related to epsilon. So we replace them all by epsilon. And you have to remember that delta t is epsilon squared. Yeah? So then here we get, instead of m, we get 2m to the power of 2m, right? Plus n plus L plus, okay, we have to plus, here's a sum from Q, this is what I've forgotten, so we also have a new parameter Q. Q is the expansion parameter of the asymptotic expansion, yeah, in which we expand the moments. So this also comes here because each moment, each expansion step will give us a new one more epsilon, right? So, and now we have the 2 divided by 2, and down here we have to go this to the power of m. Now it's not 2m, it's just m, yeah, because, you know, it's the half by the power of m, plus n plus L. So this goes into dtm, dxn, and dyl. And now we have here the Q order, A plus N, so the rest is the same, plus L, 1 minus 1, N plus L plus M, minus omega A plus N and B plus L divided by 2. This is 1 plus minus 1 N plus L plus M, and closing all the brackets. Ugly equation. Can we make it more beautiful? Now comes a very important step. I know this is all tiring, but this is one step that that is important for understanding this. This epsilon is an arbitrary parameter. This means this is supposed to work for any resolution, right? But we have any resolution only if epsilon is larger than 0. So the smallness parameter never goes to 0, it only approaches 0. So if it is arbitrary and it is not 0, then there is and the entire thing is 0. Then this is 0 for all, it has to be 0 for all choices for epsilon, which for all epsilon not equal to 0 or larger than 0, but also for the negative it is the same condition. This is only the case if each order epsilon by p is 0. Yeah? You agree? Or should I explain? I should probably explain. So say you have an equation a plus b epsilon plus c epsilon cube squared. Yeah? So, and now epsilon larger than 0 is arbitrary. Then this equation should always be 0. And if epsilon is arbitrary, then this will only be 0 if A is 0, it's only always 0 if all of these guys are 0, right? Yeah? And this is what we call equating coefficients. Equating coefficients. So, which means that we can actually get rid of this epsilon because all the occurrences of the same order of epsilon has to be 0 on itself. So from this big series, we actually now get we turn a series into what is the other thing? A sequence. Yeah? From a series to a sequence. So actually we can now write this like this. 0 is equal to m n L is equal to 0. And now this Q must be P minus 2m minus n minus L to infinity. So this means that it's always, we take out the case, yeah, where the epsilon comes to the same power, m factorial, n factorial, L factorial, 1 divided by 2 m plus n plus L. Still we have to write a few things, dt by the power of m, d, or the n's derivative, the L's derivative, and now comes m, a plus n plus b plus L, and this goes of the order q, 1 minus 1 n plus L plus m minus omega a plus n b plus L of the order q, 1/2, and this into 1 plus minus 1 n plus L plus m. Okay, so this is the big equation that comes out here. So from this equation, and you came late. This is why I'm taking also a little bit of overtime today. From this equation, we can now actually solve our derive our partial differential equations. So we have to make one assumption here, namely that omega b q is equal to omega MAB q, so is 0 for all the q's that is smaller than 0. Yeah, so we only have positive. The sum starts from 0 and not negative. So now what we can do is we can choose this p here and we can choose it to 0, which means we are looking at the equation for epsilon 0, and if we plug 0 in all of this, what comes out is just omega AB to the power to the order 0, and this is equal to 0. Now the first discovery is that the change in the populations at the order 0 is 0, right? So then we can go to the first power in epsilon, so epsilon to the first power, and evaluate this equation. So we can do this also with computer algebra. That what comes out is the first derivative of this guy, order 0, dy m a b plus 1 of order 0 minus omega ab order 1, so this is not an n, this is a 1, is equal to 0. Now, because these things here are order 0, they are const. Const means they are not dependent on anything. So they are order 0, they are const, so they will disappear. Yeah? So you take the derivative of a const value, they disappear, which means that also to the first order, the change is 0. So they will also disappear. Trying to get this whole thing a little bit more interesting, going to p equal to 2, which is the second order in epsilon. There we get dt MAB to 0 order. Again, this is a constant, so this will disappear. Plus dy MA first order. Okay, why do I write it this way? I don't know. Plus dx, usually I write x first. 1 a plus 1 b minus omega AB, the second order is equal to 0. So because this is constant, this is 0. And the last version that we are using is P equal to 3 epsilon to the power of 3 will give us dt MAB to the first order is d plus dx MA plus 1. Second order A plus 1, B plus d y M A B plus 1, second order minus omega AB to the third order, and all of this is equal to 0. So these are all of them that we need. With them we can solve our problem. So let's be a little bit more specific. We take epsilon to the power of 2 and A equal to 0 and B equal to 0. So, and this means we are looking at this equation up here, which will give us dt m00 to the 0 order, which we've already said is equal to 0, plus dx m10 first order plus dy m01 first order minus omega 00 to the second order. Now, the moment m00 is the density. The density, the mass is conserved. The density does not change in collision. This means this here is 0 because it's conserved. And all of this is still 0. So this m00 is rho 0, this is const. So also disappears. So what we end up with is m101 is equal to rho 0 ux1 plus rho 1 ux0. And this ux0, this obviously is also 0, yeah, because this is also constant. This is before the solution, right? So the solution is u1 and not u0. So this must be 0. And the other guy is this here, uy first power plus rho 1 uy0. So obviously this is also gone. And all of this together gives you dx rho 0 ux first order plus dy rho 0 uy first order. And this is equal to 0. And this can be written as rho 0 because it's a constant into divergence of u first is equal to 0. And this is our first equivalent PDE. Okay, that's not quite enough. We also need the Navier-Stokes equation. And this we get out of epsilon to the third order. A is equal to 1 and B is equal to 0. So this gives us equation 6.6 dt m1. So m10 first order, the time derivative of this, dx m20 to second order plus dy m11 to second order minus omega 10 to third order. So now this would be the momentum equation in the x direction, yeah? And the BGK collision operator, so first of all we have MAB, so this again was this definition here, and the collision operator is MAB, asterisk is MAB before collision plus omega MAB equilibrium minus MAB. So this we could also call equation 6.7. And yeah, omega AB is equal to omega MAB star minus MAB. So if we put this into the above equation, then we get, or we could write MAB is equal to MAB over bar minus omega AB divided by 2, and MAB star is MAB over bar plus omega AB. So in this way we can replace in this equation here, we can replace MAB and MAB star with the things that we actually want. So 6.7 means we have MAB over bar plus omega AB half equals to MAB over bar minus omega AB half plus omega MAB equilibrium minus MAB plus omega AB half. And this we can solve for omega AB is equal to small omega MAB equilibrium minus MAB over bar plus omega AB. So you see again, this is implicit, but we can make it explicit by rewriting it as MAB over bar equal to MAB equilibrium minus 1 over omega minus 1/2 omega AB, which we put in the equation 6.6. And if we do this, we get dt rho 0 ux first order plus dx. Now here we have to put in these replacements, so the equilibrium minus 1 over omega minus 1/2 omega to 0 second order plus dy. Here comes the moment m11. Equilibrium to second order minus 1 over omega minus 1/2. And here comes omega 11 second order. And all of this minus omega 10 to the third order is equal to 0. Now we need to know what are the equilibria. The equilibria, and this is something that we derived already several times. So now we write this here with the theta, with the velocity, with the dimensionless velocity, temperature at theta rho to the second order and ux to the first order square. A term first order square is a second order, right? Yeah. And rho to the 0 order, and M11 equilibrium is ux first order to be more accurate, this should be equilibrium to the second order, but this doesn't really matter. Where have we ux, uy's first order. So together they are again second order. And this gives us the equation 6.8 dt rho 0 ux first order plus dx rho theta second order plus ux first order square rho 0 order plus dy ux first order uy first order rho 0, and this together with minus 1 over omega minus 1/2 into dx omega to 0 plus dy omega 1 to second order minus this guy here, still remaining, and all of this equal to 0. Now we have to do, sorry for taking the overtime, we have to determine what these guys are, yeah? And these guys are determined as epsilon by the power of 2, a equals to 2, so we are now determining this guy, and b equal to 0. This gives us dt m20 to the 0 order, because this is 0 order, this is going to be 0, dx m30 first order plus dy m21 first order minus omega 20 second order is equal to 0. And this we can solve for omega being dx m301. We are approaching the end, but I still have to, it's a very bad position to stop. So because it's first order, we can replace it by the equilibrium. And the reason why we can replace it by the equilibrium, so this is supposed to be y, m21 equilibrium first order, is that since anything, because to the change, omega to first order, we have identified this is 0. So this will now disappear. So, and this M30 equilibrium to the first order is equal, because of the aliasing, yeah, this is an alien, and so this will be rho to the 0 order and ux to the first order, and M12 equilibrium first order is theta ux first order, and M21 equilibrium first order is theta uy first order. And all of this we put into 6.8, and this gives us 0 is dt rho 0 ux first order plus dx theta rho square ux first square rho to 0 order plus dy ux first order uy first order rho 0 minus 1 over omega minus 1/2, take the phone, dxx ux first order rho 0 plus dy theta ux. See, deriving the Navier-Stokes equation from scratch is always a lot of work. Plus, so there's something missing, dx y 2 u y first order theta 0 order, and still we have to have this one guy here. Now we'll take everything under this and call this A, and this A is rho to the 0 order theta dxx ux first order, we're almost done, plus dy y ux first order. Now this is something that you have in the Navier-Stokes equation, right? This is what you want to have there. And then there is a part that you don't want to have there. And this is dx ux first order 1 minus theta rho 0 plus dy y2 u y first order theta rho 0. And this what we don't want to have, this we call B. So B is equal to 0, and since we have that this guy, this have we already derived, this is 0, yeah? So we can identify that we can make this 0 if we have 1 minus theta is equal to 2 theta, and this means that theta is equal to 1/3, which is exactly what we usually use. And so we get finally, oh my God, with almost 10 minutes, no, it's more than 10 minutes late, but you were also late. We finally get to the Navier-Stokes equation. Let me write down the Navier-Stokes equation. dx u x first order square rho 0 plus dy ux first order uy first order rho 0 order. So all of this we put on the left-hand side and call this this is the material derivative. And all of this is equal to minus dx rho theta rho 2, not the 0, so the second. And this, so the second order of density times the dimensionless temperature, this is the pressure. Then comes plus theta rho 0, 1 over omega minus 1/2. This we identify with the viscosity. And this goes into dxx ux first order plus dy y ux first order. So this is ux, the Laplace of ux, and this comes with 1 with this, still this theta 1, 0, 1, and this is the body force. And all of this together is the Navier-Stokes equation in x direction. Okay, thank you for staying here till the end. I stopped the recording.